Hello students, in this video we'll find the generating function for the Legendre polynomials. Let's recall the Legendre polynomials satisfy the recursion relationship that Pn plus 1 of x is equal to times n plus 1 is equal to 2n plus 1 x Pn of x, and then minus n Pn minus 1 of x, with the initial conditions that P0 of x is equal to 1, and P1 of x is equal to x. Okay, like that. All right, good. And so now what I want to do is I would like to find the generating function for these Legendre polynomials. So now our goal is to find a function f of x and t that has the form, the sum, n goes from 0 to infinity, Pn of x t to the n, where x is between -1 and 1 and t is between -1 and 1 as well, right? So in other words, we'll have to find the radius convergence of this series at a later point. And this over here, this function is called the generating function for the Legendre polynomial. So this is called a generating function. Okay, and so the typical idea for how we find these generating functions is to use the following. So I'm going to actually write out the first term in this expansion. So what does f of xt look like? Well, when I have n equals 0, that's just p0 of x. And so the first term is going to be 1, and then the sum is going to start from 1 to infinity of Pn of x t to the n. That may seem like a silly step to do, just pull out the first term in the series, but now what I'm going to do is I'm going to shift this second sum over here. So this is going to be 1 plus the sum, n goes from 0 to infinity, and then if I subtract 1 over here, I have to add 1 to these indices. So I have a Pn plus 1 of x t to the n plus 1. Now I can use our recursion formula, right? So now what I'm going to say over here is that this expression is equal to what? So now this will be equal to, this is equal to 1 plus the sum, n goes from 0 to infinity. And then the first term I'm going to get is this term over here divided by n plus 1, right? So then the first term we're going to see is we're going to see a 2n plus 1 over n plus 1 x, and then Pn of x, and then this is times t to the n plus 1. So that's the first term we get from this Pn plus 1, is this term over here. Then I'm going to have minus the sum, and I'm going to leave this blank for a second to figure that out. I'm going to have a what? I'm going to have a negative n over n plus 1, so I'm going to have an n over n plus 1, a Pn minus 1 of x, and then a t to the n plus 1, like that, okay? So in other words, f of xt can be written in this form as well by my recursion relationship. Now the key feature in this is to do two things. The first thing I'm going to note is that I can write this expression over here as 2 minus 1 over n plus 1 by division. In this term over here, now let's stop and think over here, because now this sum really starts where? This sum really starts at 1, because when n's equal to 0, there's nothing there, so from 1 to infinity. So those are my limits of integration. And then secondarily, this expression can be written as 1, and then minus 1 over n plus 1, like that. Good, okay? Now what I'd like to do is I'd like to pull out some terms over here. But before we do that, we're going to try to shift those terms. So what we'll do is we'll do a couple things simultaneously. So this is going to be equal to 1. Now look at this first term. I have 2x Pn t to the n plus 1. So I have a 2, an x, an extra t, and a Pn. That's exactly equal to what? That's exactly equal to this expression over here with an extra t, with an extra x, and an extra 1. So I'm going to pull out a plus 2xt, and then fx t from that. Great. And then what's left over is going to be minus the sum, n goes from 0 to infinity, of 1 over of, let's see, we're going to have an x, then we'll have a Pn. I'm going to suppress the x on that. Well, let's just leave it over there. Over n plus 1, and then t to the n plus 1, like that. So that's the term we have to figure out. And now over here, what can we do? We can shift all these terms. I can take this n and replace the n. I say n goes from 0 to infinity, and replace all the n plus 1s with n plus 2. That will turn into an n, and that will turn into an n plus 2 over there, right? And so now let's look over there. So what will happen over there? on that first term, I'll have a negative, then the 1 times Pn times t to the n plus 2. So there's 2 extra t's over there. So that first term over there, this 1, is going to correspond to a what? It's going to correspond to a negative t squared. And then I'll have a what? Then I'll have a Pn and a t to the n. And that exactly gives me what? F of x and t, like that. Excellent. And then what's the last part of the sum over here? The last part of the sum is going to be a plus now, because minus minus, plus the sum, n goes from 0 to infinity, of Pn of x, t to the n plus 2 over n plus 2, like that. Okay? Excellent. And so now what? And so now we have to figure out what these sums are going to give us over here. These two sums which I have not written in terms of f yet. Okay? So let's go back now and figure those out. So this is going to be a what? This is going to be a 1 plus 2xt f of x t minus t squared f of x t. And then look at this sum over here. This sum over here with a negative sign, what's that going to be equal to? Well, this is t to the n plus 1 over n plus 1 is the integral with respect to t of t to the power n. Okay, so what this thing is over here is this thing is going to be negative x, the integral from 0 to t of Pn of x of the sum just going to be what? Of just f. Now, what would be left? I pulled out the x and I have a Pn and then t to the n integrated, so that's going to be an f of x tau d tau, where tau is a dummy variable of integration. So that's exactly what that term is equal to. It's an antiderivative of my generating function. And then similar over here, what do we have? Well, if I had Pn of x t to the n plus 1 integrated, that would be the integral of t times f. So then this next term over here is plus the integral from 0 to t of tau f of x tau d tau, like that. So stop and think about why that makes sense over here, right? So if I just had, so I pull the x out, if I had a t to the n, that would just be f. But what I have here is I have an integral with respect to t of that function over there. Excellent. And so now we're in a great shape, because now I can do is all this expression is equal to f. So I have an integral equation for the generating function. And now I'm going to put everything on one side. So this tells me that f of xt, I have one of them over there. I have negative, I have a 1, then a minus 2xt, and then a plus t squared, like that, is equal to what? Is equal to the integral from 0 to t. And now I have a tau minus x, f of x tau d tau, and then there's an extra 1 over here. So plus 1. Great. Now what we're going to do is we're going to take the derivative of this equation. So let's differentiate this equation. So now over here, what we're going to do with this equation over here is we're going to take this whole thing over here, and we're going to do d by dt of the whole thing. D by dt of the whole thing. So it's really a partial derivative, but I'm just going to write d by dt. Okay? So if we do that, what's going to happen? I'm going to suppress all the variables now. I'm going to have ft times this function, 1 minus 2xt plus t squared. And then I have f. And then the derivative of this function is like to see, which is 2t minus 2x. So f times 2t minus 2x. And if we do the t derivative of this side over here, the 1's going to go away. So this has to be equal to what? This has to be equal to, I plug in t over here, I'm going to have a what? I'm going to have a t minus x. So a t minus x over here. And then finally a what? And then finally a f of xt, f of xt. Great. And so, of course, I can subtract that from this. I have a t minus x and a 2t minus x. So this is exactly equivalent to saying that ft times 1 minus 2xt plus t squared is equal to the negative t minus x, and then what? And then times f, like so. Okay? And I'm going to write this in the following way. I'm going to write this as ft over f is equal to what? Ft over f is equal to negative, and I'm going to do is I'm going to put a 1/2, and I'm going to put a 2 back up here, so 2t minus x over 1 minus 2xt plus t squared, okay, like that. Of course, this is the logarithmic derivative of f, and this is what? And this expression over here is the logarithmic derivative of 1 minus of what? Of the square root of 1 minus 2xt plus t squared over here, right? So in other words, this is d by dt of the log of f. And this is 1/2 d by dt of the log of this thing over here. So I can write that as the log of the square root of 1 minus 2xt plus t squared to the negative 1 power, like that, prime. Okay? So those two functions have the same logarithmic derivative, right? And so that says that f is what? So now we get the conclusion that f of xt is going to be some constant over the square root of 1 minus 2xt plus t squared, because if two functions have the same logarithmic derivative, they agree up to a multiplicative constant. And what's that constant going to be equal to? It's a constant which depends on x, but what will that constant depending on x be? So there really should be a 1 up here. On the top, there should be a c of x. And what will that constant depending on x be? When I plug in t equals 0, I have to get 1, right? Because when I plug in t equals 0, we get 1 over here. So when I plug in t equals 0, I have a square root of 1 in the denominator. So the constant that goes on top is just equal to 1, right? So in other words, this function, f of xt, if I Taylor expand this function in terms of powers of t and whose coefficients depend on x, they will generate the Legendre polynomials. And now we want to stop and think, because this function appears very, very frequently in mathematical physics in terms of gravitational potential and electrostatic potential. And so in further videos, what we'll do is we'll look at this function carefully, which generates the Legendre polynomials, and then consider that in terms of a problem of finding the electrostatic potential between two charges. Thank you very much.